Sure, good afternoon. I hope you all do well in your exam. So any other comments? I was chatting with a few of you at the first row. So any additional comments about the exam? Too long, too difficult, or any particular topics we found we need more additional attention? Any thoughts? Yeah. So all right. Any thoughts will be useful to improve. But we have 2 more exams to go. Yes.
I don't know if I just did the math wrong, but I did the math for the last question. It was like the hypothesis test one.
Right.
I feel like it was kind of like how to calculate.
Okay. Yeah. I heard some of the some people complain about that, but
Like it's doable though. Compared to the practice, the one on the practice exam was like the Z-score was just like 2.
yes. Yeah. Yes. So yes, I understand, because each time we try to make those question to be as diverse as possible, so to give you no clue, so you can't catch any clue from past exams. So actually we put different people to design each question. Yeah. So sometimes more experienced people will try to give you a much simpler Z-score. Some people a little bit tough. Yeah, but we do our best to polish those exams. We actually, as I mentioned to the gentleman, we actually put a lot of UTA to take this exam before to timing it. And actually we remove one question before the exam, like a few minutes, 10 minutes before the when we sent for printing, to save you some time. Yeah. Yes, question. Okay. Some extra time for name. Yes, absolutely. That is a great one. Yeah. Yes. Sorry. More time. Okay. Yeah. I think so. Yeah. We do fear this exam is a little bit longer than we are hoping for. Yes. Yes. Yeah, absolutely. I think but we will have some some rubric and we will define what will give you partial, what will not. So try to be fair across all 3 sections. Yeah, but definitely there's a partial credit. Yeah. Any comments? Any suggestions? Is any like a particular question you feel you better hear more during the lecture, or is any? Yes.
I think there's specific programming questions that use a very specific function. It was like all about the set function, which like I didn't like specifically see that much in lecture. I think it would have made either if you could see that more, or if
which one? So sorry, just repeat one more time.
There was a programming question where like the whole question was based on the set function, which is like some imported function that we have.
Oh yeah. Okay, so okay.
Or anything.
Right. We include that during the lecture. I think that we didn't have the practice the examples for the set. You mean to try to using the set to find some unique to remove this redundant that. Yeah. Okay. Yeah. That makes sense. Yeah. So yeah. Yes, probably I should mention, but it's on the slides first of all. Yeah. So I should mention a little bit more. Yeah. Because actually, yeah. So you're right. So yes.
just have a question in general. Where can I find the cutoffs for the grades? I looked
So we will decide that at the end of the end of the course, but we will. Yeah, so in general, we were more or less around that. For example, it's not a hard cutoff. Usually we will say things, for example, above 95 will be A plus, above 90 will be A, but will be something around those. Maybe we're plus minus 1 point based on the, because we want to keep certain proportion. Yeah, but we will make sure at least we will do our best to enforce the same cutoff over all 3 sections. So at least you get the same score, you will get the same grades. Yeah, so this is one thing we will do. And sometimes I'm still talking to the other 2 professors. We are thinking to say whether we want to curve a little bit to make sure you guys will get a fair treatment compared with the last semester, because different year we have a slightly different, maybe we will control the difficulty, but there's no scientific way to really say. So we will try to make sure, let's say your average will end up around certain points. Yeah. We will do our best. I mean, we're not like in a perfect way, but we will try. So yeah, great. Actually, when I go through this, I feel it's not easy, but it's also it's doable. So if you really think you know the content, the only thing I worry is whether you have sufficient time. If you had enough time, I'm sure most of the question is easy to fix. Yeah. So great. I mean, if you have any additional comments, feel free to send to me, and we would love to have those comments and improve over the exam 2 and 3. Also about the format, the exam, the way we conduct the exam. Is any? Some people say we need have more TAs be there to collect paper. Looks like it is a long line. Okay, yeah, this is a we will definitely improve that. Yeah. So other than that, is any suggestions about the exam format? I think the more times to write the right name and shorter line for collecting your paper. Any other suggestions or well, yeah. Anyway, just you can send me individual emails if you have some particular thoughts. Yeah. Great. Hope in general, I hope you enjoy this course so far. Yeah, this is a very useful class, I would say. Yeah, I think that everybody should learn some kind of data science. Yeah. I think I attempt to talk about this twice, but every time is near the end of the class. So let's today finish the confidence interval and see how far we can go. So as I mentioned, you have many different ways to understand the confidence interval, but in general, the way I usually think is to say if you think at the beginning, right, you have a bar. If you remember at the beginning, you have this kind of picture, right? Then I put some of this range there, right? So this is a figure usually you will see, right? In a paper or some magazine. So how do we interpret this one? So usually, at least my way to think about this is to say, if you, let's say from a sample, you get your sample mean X bar, then I will try to ask you to find a range around my X bar, so that there's a 95% of the chance your true population mean will fall into that range, right? So let's say if we find this blue line will be the this upper and lower bound of this interval. So then you will say all the possible, let's say the true population is those dashed line. If you think any of them can be potential the true population distribution. We don't know that. Yeah. But let's say if you know all these are possible, the population distribution, then if you take any of them, you will find the true population is around this rate, right? If you are very close to the rate, of course, you don't have anything to worry, right? Because they will be there. The only things we care is what will be the boundary. If you move out of the boundary, then this 95% of confidence will no longer be satisfied. Yeah. So how to find that extreme value? Do you get the meaning, the intuition behind? Yeah. So why we need this two blue line? So as I mentioned, you can always define the C% of confidence interval, but I try to make it more concrete. I will keep saying 95, but this 95 can be replaced as, let's say, 90% of confidence interval, 98% of interval. This is up to you. Yeah. So let's using 95 for now. So my interest is to look for a 95% of confidence interval, and that essentially try to say this area is 0.595. Okay, because they are symmetric, right? Try to see whether this makes sense to you. And this is equivalent. This is equivalent to say, this is my X bar, and this is my, of course, the population mean. If we think back in the hypothesis test, that picture. Yeah. So this is essentially to say, this will be the symmetric corresponding part to my X bar, because when you have your X bar, you can find the symmetric one. So essentially, I want to make sure this region is equal to 0.95. If I want to look for the 95% of interval. Okay. Why I try to see this? This is come from this picture, because I want to find the boundary, and such that after you define the boundary, my true estimated mean or X bar is not too far from you. Is to make sure the region here is half of the confidence interval, because you have another symmetric region which define your upper part, right? I hope that makes sense to you. Does that make sense to you? Yes, questions?
Is that area underneath the tails?
Sorry?
Are you also calculating the area?
The tail? No, just to this part. Yeah. Because the 95% of, if you go further, you will get more confidence. Let's say if you want to 98, probably I will take a little bit more of the tail. Since you say 95% of confidence, I want to get the center part. Make sure the center part to be 0.595. You see? Yeah. Yeah. So the reason I try to draw this picture is because I want to make the mathematical calculation become more intuitive. So first of all, I want to just try to show you the procedure to compute the confidence interval, because so far we talk a lot. It's just I want to make you be clear what is confidence interval, why we need it, what is the meaning. But now After all, we need a way to compute. Okay. So the procedure is to, first of all, find the z-score for this guy. Right? This is what we have seen before during the hypothesis test, right? You get your x bar. You want to find what is a z-score of this x bar. All right. But now the difference is during during the hypothesis test, we know what is the mu. We know because you are given the population mean, and then you calculate the z-score for the x bar. But now it's different. Now I will tell you, I want this value correspond to a z-score, which makes sure this region to be 0.95. So see the difference, I hope. Yeah. Right. But still, this is doable because we will use this guy to calculate. Take a look. Spend 5 seconds to look at this formula to see why we are doing this. The C here is the 0.95 in my example. Okay. Why are using 1 minus 0.95, then divide by 2, then again I'm using 1 minus that. Why? Think about that. See that, does that make sense to you? Take a look at this, the formula. So why this makes sense is first, I tell you this shaded region is 0.95, right? If you remember the previous picture, you have symmetric upper and lower, so which convinces this is a equivalent way to look at this problem. So this is so now my C equal to 0.95, but when I using 1 minus C, that is what? That is this two-tail region, right? Right, using 1 minus C, which is a 0.05 in this case, is this tail region, right? Then I divide by 2, that means it's one of the tail region, right? Does that make sense? Then I using 1 minus that, I will get these whole things, right? Everything from here to here, everything to the left of this x bar. Does that make sense? Right? So now, if I using this PPF, is go from probability to z-score. I tell you, I want to calculate 1 minus 0.95 divided by 2. This is my probability, which is C is your cumulative distribute the CDF up to this x bar, up to this line. So everything till this. So I use that to compute a z-score corresponding to this point. This will become, yes, questions? Yes, confidence interval is two-sided. The reason is, if this is what the red line is what you actually have, you give a bunch of sample, you get one. Then I want to tell what is the interval. Of course, you can be a little bit larger or a little bit smaller. You want to look for the two boundaries. Yeah. Then when I say 95% of confidence interval, you need to divide into 2 regions, right? Up larger than you, smaller than you. But this figure is equivalent to this figure to think about this guy, right? So this formula essentially to find the z-score to this point. And then it's very simple. Now you have you know what z-score I should have for this guy. And then I will plug in into my, because I want to combine to compute my boundary. I want to compute this mu is what I want to get, right? The current mu actually is my is my boundary, right? Is the boundary of your interval. During your hypothesis test, you know the mu, and you want to compute the z-score for your x bar. But now what you have is x bar. You want to find where is the right to set the mu as your boundary to make sure the in between is at least is a half of your confidence interval. Okay, so if I have this, then the rest is just some algebraic manipulation, right? Because this is you have two-sided, remember. So you will convert this guy into plus and minus version of this x bar minus mu and sigma divide. Since you have plus minus, actually you will get a range. Do you still follow? Right. It's straightforward, right? So actually, I talk so much. Maybe you will feel I waste your time, because during the actual situation, what you need to do is the last step. You don't need to really go through so many intuitions, so many understanding. You just need the last step, because you see what I mean, right? Because this is a x bar is what you have, right? You get a sample, you measure, and then this z score is pretty fine, because if you say c is 95, the z score is already defined. You already know what is the z score corresponding to a 95 to c, sorry, not 95, corresponding to c take 95. Yeah. Anyway, yeah, so it's predefined. And this is also is know, right? The sample, how many sample you are used to compute your x bar. And this sigma also is known. It's your population variance. Of course, you can estimate from sample. So basically, give me x bar, give me some of this parameter, your distribution parameter. I can right away write down the confidence interval for you. All right. Does that make sense? So please, yeah, if some part which doesn't seems obvious to you, please just ask me. I can repeat. Are we fine with this confidence interval? It's a very mysterious concept, but it turns out to be pretty straightforward. All right. So yeah, if you define everything, predefine everything, let's say you know what is your variance, you also decide the number of samples, and this is your x bar. And when you have an increase c, you need to enlarge your interval, right? This is pretty obvious, right? Because if you have a Gaussian, if you want to take this region, of course, this is a smaller c. If you want to go to this, your c will increase, right? Because this corresponding to a likelihood. Right? Then you can go to this range interval. This will even larger. Yeah. So yeah, of course, this is. I hope when I draw this, I hope you get what I mean. But this is actually the correct version. You should think in this way. Yeah. But essentially, it's the same thing. Yeah. But this is a more right way. You have x bar to your red line, then you can think about the range in between these two blue bar. Need to increase to get your beta interval. But essentially, mathematically essentially equivalent to my simplified version. Okay, so now we are back to our original example. So let's calculate 90, 95, 99 confidence interval for mu. Okay. So now let's recall. We have a X bar 95 gram, and then we have a sigma, which is our population variance. Then we have a n equal to 100, which is our sample size. So assuming you take 100, let's say, widget to measure the average weight. Then we will ask you what is the confidence interval for 90%, 95%, 99%. Try to write the corresponding interval. So as I mentioned, what you need to do is simple, super straightforward, just plugging into this formula, right? This formula essentially is this guy. This formula, just plugging this formula. Then you say you replace your X bar here, then replace your sigma here, replace your n here. The only thing you need to change is the ZC. You will write your interval in terms of a ZC function. So what is ZC? The ZC will depend on what confidence level you want, right? When you have 90, your ZC is 1.6. 95, you correspond to this, 99. So basically you change your different ZC. So then you will replace with corresponding ZC, you will get a different interval. Yeah. So yes. Yeah. During the if you are during the exam, probably we will give you, we mostly will give you something corresponding to the 3 sigma rho to make it easy for you to calculate. Yeah. So are we fine with this confidence interval? Any questions? If no questions, I will proceed. Okay. So I think that we keep mentioning the Z test is you need to if you do not know the the standard deviation, you need to estimate it from your sample. But usually there we assume we have a sufficient size. Okay, usually we say n greater than 30. So what happens when you have a much smaller sample size, and also you do not know the population standard deviation? So in that case, we need to replace the Gaussian assumption. So basically, we were not using the Gaussian distribution. We will replace that with something we call students T distribution. And then we will convert our Z-test to a T-test. When we apply T-test, is this. If we do not know the sigma, when n, let's say, smaller than 30. Okay. And the student t-test has a very similar shape with a Gaussian, almost similar shape, but you can find is we call has fatter tail. Yeah, so the outlier is punished less, so you're a little fatter. Yeah. So basically, you try to give more weights to the distribution away from the mean. Otherwise, I would say the remaining is more or less similar. When you call the function, you need to pay attention. There's one additional parameter of the distribution is the degree of freedom, which is n minus 1. Yeah, when you're using the function, using this distribution, you need to input this one additional parameter. But otherwise, I would say the procedure is more or less very similar. Let's take a look. So if we want to do this t-test, first we will try to find the standard deviation of the sample, and this is what we try to compute. I think that we probably have one question during the exam. I'll ask you to write the code for this. So this is a standard way to compute the standard deviation, and then we will compute the z-score, right? So this is exactly the same as what we are trying to do with our z-score. So now we are computing the t-score. Then after we have this, we are plugging. We will try to compute the p-value. The p-value now, we were using the t. Before it's a dot norm, right? So now we will have the dot t. Then you have the ABS. You have the degree of freedom. This df is the extra parameter, which is n minus 1. Yeah. So this is only difference. All right. And for the confidence interval, it's also very similar, right? Before we have norm.pbf, now we have t.pbf. So this is exactly the same. 1 minus 1 minus c divided by 2. Okay. But you need to input the degree of freedom. All right. So almost identical to the normal distribution, but just we take a more fatter tail distribution to replace the Gaussian distribution. Are we fine with the t-test? Yeah, almost repeat the exact steps. Yes. Yeah. So as I mentioned, if you have a smaller number of samples, if you use the z-test, you need to estimate the standard deviation from the sample, which is not very accurate. Yeah, and so in that situation, when we use a t-test, we will put more weights to those tail region, to those outliers. Yeah. Because remember, if you only have a small amount of samples, it's very dangerous to assume those outliers to be true outliers. Right? So you need to be a little bit conservative to say things far away from the center. All right. Yeah, so far we are talking about the two-sided test, right? We are talking about whether your sample mean is the same as your population mean, right? So smaller, larger, we care, but sometimes we only care about one direction. For example, our non-hypothesis is to say, is my population mean will be smaller than 100. So I just only consider one direction. All right. So then my alternative hypothesis will be greater than 100. So basically, this is a like one direction checking. Okay. So in that case, we will use this one-sided or one-tailed test. So now, how does the p-value compare between 1 and 2. Remember before, during two-sided, if I have a p-value, I divide by 2, right? So 2 region will contribute to your actual p-value. So any given data points has half the p-value in one-side test than it does in the two-side test. And we do not divide alpha by 2 for one-side test because all the area now is in one tail. So I hope this is rather obvious because now we only care about one tail region. All right. So again, we have a lot of simple extension. We can use, for example, use how about do two sample t-test? Yeah, just in your brain, think about how to do that. The reason we say simple extension because they are rather obvious the procedure. Yeah. So for example, how do you do two sample t-test? Right. Start to think. If you find it's confusing or you don't have any idea to do this, you can raise your hand. We can talk about. Otherwise, we just go through them together in our brain. And also, can we build a confidence interval around mean when the norm approximation is violated? For example, using the t-statistics in place of the z-score, right? That's possible, right? Because we just see how to compute a z-score from a t distribution, right? So those are, of course, those only will be used when you have less than 30 samples. So for example, you have less than 30 samples, you get your sample mean. I ask you to construct a 95% of confidence interval. Maybe you will need to for using the t-statistics to start to compute your boundary, right? Compute your the t-score, right? I hope that makes sense to you. Are we fine with that? So what if we only interested in a confidence interval on one side? So I hope that this is also, you can try to do this exercise by yourself. Try to think, can I use the what I have learned to come out with this? Is a kind of straightforward, yeah. So if we take a one-sided interval, try to think how to do that. Probably one of the boundary will replaced with negative or plus infinity. Then when we compute the z-score or t-score, then instead of this guy, we only need to consider this guy, right? Because we only care about one side. Does it make sense? So we finished this hypothesis and confidence interval section. Any questions about this? If not, I will quickly jump to some file operation. Any questions about the confidence interval? So confidence interval we are mostly going to exam 2. Yes. So we need to have some good intuition in order to not forget about the calculation. The calculation is very straightforward, but the more important is try to understand what is this concept and why we need this, how this formulation come out, what's the math, the simple algebraic manipulation, why in that form. Yeah, those things will help you to remember this forever. Yeah. All right, let's do this. we only have a few slides talking about the Python file IO. In any programming language, right? If you know C, MATLAB, Java, you have to deal with file, right? You have to, a lot of time you need to open a file, then read the content inside, and probably write back something. Yes, so this is because if you don't have a file, everything you compute will not be saved to your disk, right? So also a lot of time you have to load your data from somewhere, right? When we play with data science, let's say we talk about 1 million element list, you have to load somewhere. Yeah. So most time you need to probably have this file IO operation. All right. So if you have any minimal knowledge about a computer, you will know when you play with a file, you need to have at least a 3 stage, right? You need to open the file, right? Then you need to read or write the file. Then you need to close the file, right? I think that I hope you have a brief. When I mention those 10, you have a brief. The actual actions happen in the computer, right? Usually you have your file stored on a disk or something. Then probably you will, when you open the file, maybe you will grab to know like where to access the file, right? At least you know what's the address to actually I can start to do the operation. Then when you read, or then probably those contents will be fetched into your memory. Then you start to work. When you close, you need to probably write your memory to your disk. Of course, a lot of optimization is doing, right? Sometimes you need to prevent you lose content from scratch. So actual file operation is more complex than that, but roughly is this. So which is reason you need to open a file, you need to do the action, then you need to close. So the close is also important because if you do not have an explicit close, whatever you have probably is in your memory, right? It's not yet saved to your file. So sometimes I think in some language you have an explicit save, like a save commands. And also the close is important to empty your space. And probably you allocate a huge chunk of the memory to operate the file. When you close, probably those things I tell the system to say this is not useful, flush them away. So there's a lot of reason why we need close the file, right? Any questions so far? So I hope you agree with those general file operation concept. So we use the open method to open a file. Then we will, when we try to open the file, a lot of time we want to specify the mode. You want to open the file for reading purpose, or you open the file for writing purpose, right? So you can do open and put a flag here. Let's say when you put a W, that means you open the file in a write in text mode. All right, you can of course replace the W here with the R to say I open the file only for the reading mode. Okay, and also there's another option called append. You will say I open the file in a append mode. So what's the difference? So when, of course, when you open in R mode, you will not try to write anything. Okay? So it's a safe way if you to prevent you to accidentally write anything. So basically you are open things in a read only mode. Then what's the difference between W and A? I think if you code in C before, I'm sure you have seen this difference. is when you open a file in W in the write mode. So when you write anything, it will try to overwrite everything in the file. It's like write from scratch or something. But a lot of time that is not what we want. We want to start write and adding to the existing file. So that is append mode. So you are start to append to what you already inside your file. Okay, so does that make sense? So both is a kind of writing, but one is a fresh away what you have there and just put my new stuff there. And the append will try to adding towards the end of the file. All right. Are we fine with these operations? All right. As I mentioned, it's important to do a close. So, for example, one of the purpose is to free up the resource and with a file. If you open a file and start writing it without closing, soon you will find you have a lot of the memory allocated but never be released. So there's another thing is we want to raise for attention is when you do the operation with a file, a lot of time you may have errors, situations happens, right? You open file and then when you perform some operation may fail, right? But if that is just like when you do a act to play some programs, the program has some unexpected crash. Then when you open a large file, this crash will lead to your resource will never be released. So which is not very good. A quick way to try to do that is we use the try to put your open command to the try and then put a finally. So this will try to say no matter what exception you are throwing, I will execute the final one. So even I have some exception happens, I will still try to do the close. Right. So this is a reason why we do this try and finally. So to make sure, yes. Try, sorry. Oh, you mean the with what open? Oh yes, exactly. Yeah, actually we are talking about during the next slides. Yeah. So of course there's a better way. Actually, this gentleman already mentioned is try to use the with. When you do with open what as f. So this is like implicitly you will handle the close. So you do not need to like doing a finally close. It will naturally handle the close. Yeah, let me see how many. Okay, so probably I will start from here next week. Yeah. So have a good weekend.
Thank you very much.
Yes.
Have you covered the GPU notebook or Hackathon?